Hello class, this is Mr. Lehman. In Unit 9 we did in the stoichiometry, which involves calculations, quantifying our chemical reactions that we learned back in Unit 8. So at the heart of our stoichiometry calculations is something that we call the mole ratio. So the mole ratio, we know that 1 mole of a substance, 1 mole of an object, is this many of it, 6.02 times 10 to the 23rd. So in order to quantify chemical reactions and figure out numbers involved, we have to always convert into the mole. We can't use mass, we can't use grams, because atoms weigh different amounts, because they have different numbers of protons and neutrons. So we have to always convert into the mole first. So we're not going to get into conversions right now. All we want to do is focus on the mole ratio and what that tells us and what that has us do. So what do we mean by mole ratio? So anytime you have a stoichiometry problem, you always have to balance that equation. So we got to make sure that we have the correct balanced recipe so that we're satisfying the law of conservation of mass, law of conservation of matter. We're not destroying or creating atoms. We're not losing or gaining mass. So if you look here, we have 2 oxygens on the left. We only have 1 oxygen on the right. So just like we did last unit, in Unit 8, we balanced chemical equations. We have to continue applying that skill in this unit. So the way we read this is 2 moles of hydrogen gas will react with 1 mole of oxygen gas to make 2 moles of water. So there's a 2 to 1 to 2 ratio between the chemicals involved in this equation. So for every 2 hydrogen molecules, we need to have 1 oxygen molecule. So you're wondering, well, why 2 to 1? Well, if you look at water, water contains 2 hydrogen atoms for every 1 oxygen atom. So it makes sense that we would need twice as many pairs of hydrogen as pairs of oxygen in order to make water, because of that 2 to 1 ratio of atoms within the water itself. So how do we apply this? Alright, so we did the stoichiometry s'mores activity to introduce what we call limiting reactants and to figure out ratios, and so this is what we're doing, what we did there. So let's say we have 8 hydrogens and 3 oxygen molecules. The question is, how much water could we make? Well, if we look at this, so there's a 2 to 1 ratio here, so 2 of these plus 1 of these will make 2 of these. So I like to look at, well, how much do I have, and compare that to what the recipe calls for. So 8 hydrogens are 4 times more than what the recipe calls for. So 2 times 4 is 8. So it's like making pancakes. If you want to multiply the recipe by 4, you need 4 eggs instead of 1 egg. You need to have 8 cups of flour instead of 2 cups of flour. Maybe like blueberries in your pancakes, you could have 4 cups of blueberries instead of 1 cup of blueberries. So all we're doing here is saying, all right, 8 is 4 times greater than the chemical equation, the recipe. 3 oxygens compared to 1, that's only 3 times greater than what the recipe calls for. So if I have 4 times as many hydrogens as what the recipe calls for, and I only have 3 times as many oxygens, I only can make 3 times what the recipe calls for. So my chemical equation says I can make 2 waters, so I could only make 6 waters, because I only have 3 times the number of oxygens as the recipe, so I only can make 3 times the amount of waters. So how much of the hydrogen would I need? Well, we triple the recipe, so we wouldn't need all 8, we'd only need 6. So that means we would have 2 hydrogens in excess, 2 hydrogens left over. If we look at another equation here, this is ethane. Ethane, hydrocarbon, burns. So we provide a spark and it combusts and burns into CO2 and water, just like we learned last unit. If I want to balance this chemical equation, I would need a 2 and a 7 and a 4 and a 6. So 2, 7, 4, 6 balances this up. So if I want to burn, this is another application, if I want to combust 16 moles of C2H6, how much O2 would I need? So this all reacts. Well, if we look here, 2 of these requires 7 of these to react. So 2 requires 7. So 16 requires how many? So how many times greater is 16 than what the recipe is? So 2 times what gives you 16? 2 times 8 gives you 16. So we have 8 times more than the recipe. So what we can do here, without looking at even differential analysis, If I have 8 times what the recipe calls for, then I would need 8 times this. Keep that same proportion to the same ratio. So 7 times 8 is equal to 56. So I would need 56 pairs of oxygen to react with my 16 ethane in order for everything to react completely with each other. And then you might ask, like, what would I form? Well, for multiplying the whole recipe by 8, 4 times 8 would be 32, so I could make 32 carbon dioxides. And 6 times 8 is 48, so I can make 48 waters. So when you look at these problems, think of it as, the recipe. Think about what you're doing to the recipe, and that will help you figure out the correct ratio. All right, so continue on to the next tutorial. We'll get into setting up some stoichiometry problems and take it to the next step.